Okay, for now, we will go to the beam design, beam or girder design, but I already have a video which is the same to this. So for the 18 story, for example, I will go here to my channel. I already have the tutorials for the gravity beam and girder discussion. So same din yung Excel na ginagamit dito. So okay, so this is number 24. Okay, this one. You can go here and there is a tutorials here. Okay, so up to using the Excel. Okay, then now we will go to shear wall design. Okay, so shear wall design. So this is for the joint. Shear wall design. We have here define peer labels and assign. So we have peer labels, that is shear wall 1A, shear wall 1B, shear wall 2A, shear wall 2B. So I'm going to ground floor. So I have here shear wall 2A, shear wall 2B, shear wall 1A, shear wall 1B, and all of that shear wall is 600 mm thick. Also, this shear wall have a different peer label. Define peer label. Okay. Define peer label. So we have here shear wall 1A, shear wall 1B, 2A, and 2B. So what is the purpose having different peer label? Okay. So meaning having different peer label, that shear wall has its own stiffness and has its own property. So for the design, the forces and the stiffness to use is for shear wall 2B alone. So it's different from shear wall 2A. So if you, for example, you define shear wall 3 and you assign shear wall 3 here and shear wall 3 here, so you will have a wrong analysis and design. Okay, because the stiffness of this and this will become one, and that stiffness will act at its centroid. So when you do the analysis in the design, you will find a wrong output. So that's why we separate the peer label. Also for this one, we'll also separate this one for the same scenario. But in case you have wall letter C here, for example, they will act as one. You can put peer label for this peer 1. Let's say this peer label, this peer label, and this peer label. You can assign one the same peer label. So it will act as a whole section. And the stiffness will here in the centroid of that core wall, and the analysis and design will be correct. So I will show it after this, before the video end. Okay. So for now, I will measure the wall if I can define only one peer section. Okay, so we have pier label, we have pier section. Okay, so we have pier section. It will define to do the design of the shear wall. So we have a pier label to define its own property and stiffness and the forces to use for every pier. And you have here the wall section. Okay, so for the wall section, we have the same wall section. All of the wall are 600 mm thickness. Okay, so I will just cancel this one. So if the shear wall having the same thickness, we can I will just measure the wall by using none. So I will just measure this one. I will click this point to this point. This is 2 meter. Is this 2 meter? So I will just remove the wall property or the pier label. Okay, so this one is, let's say this one is 3 meter, then this one is 3 meter. So the section and the geometry is the same, so I can assign them as one pier section for the design. Okay, so this all are the same. So for example, but in the pier section you can do the different pier sections. Okay, so I will just select the object type. So select object type. I have wall, show selected objects only. Then in 3D I have this wall. Okay, so now I will define pier section. For example, I will define different, because now we have already defined a section. So I will define, for example, this definition is not exist. Okay, so we will add pier section. So let's say this is shear wall 2A. So I will shear wall 2, let's say shear wall 2, foundation to third floor. Okay, so existing from, let's say, ground floor, and this is shear wall 2A. So this shear wall 2A is this shear wall in the model. So now I will check the section designer. So this section designer will give you the geometry of this one. Okay, because you select the shear wall 2A. So if you select the shear wall 2B, you will also find the geometry of shear wall 2B. Okay, now at this point, this is 0, 0. So you will see the 0, 0. And if you hover to this point, you will now get the Y600. So the thickness is 600. Okay, then the length of the wall, if you hover to this point, you will find X is 3000, meaning the length of this section, pier section, is 600 by 3000. Okay, now we will define the rebar here. So we'll define. So for example, I will do the CNT section, or for the shear wall, because in the elevation, let's say this is the elevation of the shear wall from floor to floor. this section is, let's say this is tension, and this section is in compression. So alternatively, it will also act, conversely, it will act also like this. So it will act reversal. So if your forces is here, so you will find tension here and compression here. If your forces is in this direction, you will be having this stress. Okay, so for this stress, we will be having a boundary element. So how to do the boundary element? So for this 8-story, the boundary element, I think this is in need of boundary element, because there is a code provisions when to use the boundary element or when to not. Okay, for this 8-story, so I will not go back to the boundary element. I already discussed it to the shear wall design for the 18-story building. Or in the code, you can find or you can read the code from NECP or ACI. So let's say we will introduce the boundary element. So I will just right click this one, and the reinforcing is, I will select no. So this will just a pure concrete. Okay, so this is 600. Let's say I have boundary element of 600 by 800. Okay, so what I will do is I will just select this draw rectangular bar, so I can put it here, and I will put the line. So I want to draw a line here, and that line is, I will select the line and edit, replicate along X. I will just say this is 800. Then maybe I can have another line. So let's say this is, I will delete this one. Okay, so I will just put my midpoint. Okay, so I have that midpoint. I will put my rectangular rebar here, and for example, I have 600 by 800 column there. So I will have to define the, let's say this is just like a column. So you have 800 here, 600 here. So the ductility check, you have to check how many legs to be used here. So that is already discussed from the previous video. So how many legs you need to put here. Okay, that is from the ductility check. So the ASH formula. Okay, then after you getting that, for example, I have a 3% rebar here. So the 3% of, let's say 3%, so 3 divide 100 times 600 times 800. If I use 25 mm, so this is the AS, and I will divide it by the pi d squared over 4, so the d is 25, so that is 490 mm. So you have here almost 30 longitudinal bar of 25 mm. So if you have 30, for example, so I will put here, this is 800, So for example, I will put here a 10, 10 rebar here, 10, and 10 here. So I have 20. Then I will put in here a 4 and 4 or 5. So this is the procedure. So I will delete this one. So the dimension of that, so the height is, this is the height, and this is the width. So considering the concrete cover, so I will just put here 420 and here is 720. So just click OK. No, sorry, 600. So this is 520. Okay. So I will put here 8, 825 mm. This is your bar diameter and this is your 8 number, and I apply to all edges. Then you have your 8, 8. Then I will, let's say I have here 5 and I have here 5. Okay, so that is the layout. So total, I have a number of, so this is 8 plus 8, 16. So 20. Then I have here 5. I have 30, 25 mm longitudinal bars. Then I will just copy or mirror that one. So I can find the X value equivalent to 1.5. Then I will just select this one, edit, replicate. Then I want to mirror that. Then general line. This is 1.5. And this is 1.5. Then I will just put 100 here. Then that is my value. Then I'll just put here this longitudinal bar. Okay. Okay. Then I will say this is 20 mm. Same to this one. So this is the spacing 150 and the okay. So I will just click OK. So then I will just click OK. I will just click OK. Then I will save this one. Now I will assign what I define. So I define pier section and I will assign it to the pier. Okay, so I will just select the 1, 2, 3. Let's say this is 1, 2, 3, and you can assign it through this assign pier section general, and you can put shear wall 2 from the section at the bottom and section at the top, then reinforcement to be checked. Click OK. Then after clicking OK, you have to save first. Then you have to run. So we'll just run this one. Then I will run the shear wall design. Okay. After that, you can check the display design info. You can check the longitudinal bar. So this is the longitudinal bar. Then you can check the pure DCR. So this is the DCR, demand capacity ratio. So this is failed. This is for the shear reinforcing. This is what you get. And for the pure longitudinal reinforcing bar, so meaning your what we provide is not enough by times 2 or times 2.5. So we will just put additional bar for that shear wall to third to foundation to third. So I will just, let's say this is let's say we have to put 4.5% divide 100 times 600 times 800. So 21,000 divided by 490, we'll have 44. So 44, you can bundle the rebar, or you can reshape this one. So up to here. So for now, we can use, also we can use, we will not relay out, but we will just increase the bar diameter. So let's say we have 32 mm, we will use 32 mm instead of 25. So the 32 mm is, I think this is 615. So pi d squared over 4 using 32 mm, that is 615. So 615 times 30 equivalent to 18,000 divided by 600 equals divide 800, that is 3.8%. 32. But if we use, let's say we will use 36 mm, so that is 804 times 30, that is the AS, total AS of this boundary element, divided by 600 divided by 800, you will getting 5%. Let's say we will make it 36 mm, but in reality you have to maintain it to 4.5 because we are considering the splicing. Okay, so we will put a 36 mm. So 36. So for the 36 mm, you will be careful to this value. You have 36 mm diameter, and you have to be careful for this area, 10.2 cm squared. So 36 mm 36 times 36 d squared divide 4 times 3.1416 1,000. I mean 1,000. So the 28 mm is the 804. So this is 1,000 mm squared. So this is the value. Area is 10.2 cm squared. So this is the value. Okay. Then I will just click OK. Apply to all edges. I will just put here let's say this is 5. in reality, you cannot put this 5 here because you will consider that one. So what to do is you can bundle this one. You have to lay out this one. Okay, so but in this presentation, this is the total number of rebar. But you can bundle it to have a adequate spacing for the actual construction. Okay, then we have a requirement of spacing from the NECP that is equivalent to, I think, 2.5 times diameter or 50 mm. Next is I will edit this one using 36 mm and just maybe I need to increase this size to 25 mm just to help the okay, then click OK, click OK, click OK. Then I will just rerun the design. Then you will go to DCR, BLDG ratio. This is 1.47. So you will notice, or you will understand that when we add when we jack up the rebar, so the demand over capacity is decreasing because we increase the capacity of this. So by iteration, you can do again to make it less than 1. For the foundation to ground, this is failed. Also for the bottom of the ground to second, this is failed. But for this pier, this is pass. So you will let it, but in this case, you will have it to increase by a certain number of bar. Okay, what to do? You can define again. So let's say this is from second floor to third floor. Then I will just add a copy. I will put shear wall 2 ground foundation to second floor. I will increase the rebar. Let's say I will increase this by let's say 28 or 32. Then this this two will be assigned different from the second floor to third floor to have a not over design shear wall. Okay, this one. Then you just you'll just save it and rerun, and you can define again using smaller rebar, let's say 25 mm or 25 mm for this upper part. Okay, that is the so the section is failing in that case. So we can increase or we can make it, we can treat it as a whole column, or this one. You can treat this as whole column. But after third floor, fourth floor, you have to define another wall. So let's say this is 1 meter. I will just delete this one. Okay, I will delete this one. Okay, so I will put it here and right click. Let's say this is 25, space at, let's say, 100. And I have also corner bar that is, let's say, 36 mm. Apply to all corner. Okay, click OK, click OK, click OK. So knowing that this one is foundation to second, link to be checked. And for the other shear wall, you have to define another, let's say, 2 to third, and or next is 3 to fifth. The rebar is decreasing. You can do it. Okay, so this, or one thing, you can increase the thickness of the wall or increase the rebar. So this is the procedure, but you have to hit the value of BLDG ratio less than 1. Then for the, let's say, I will check if the thickness is adequate. Control table. You will go to design, shear wall design. Then it will give you here a warning. Design inadequate because of the this ratio is more than 1. But the shear reinforcement, this is your shear reinforcement. You can convert it to, let's say, this is your in plan, this is your wall, this wall. Then you have here rebar. This rebar indicates by this rebar. Okay, so the spacing per meter, you can now get the spacing per meter. Okay, the spacing parameter is just like this. Area of rebar, let's say 5,000. So you will find the spacing using diameter and using number of legs at each face. There are two, and there you have, let's say, you have this area of bar, then you will find the spacing. Okay, so that is the how the shear wall being designed here in the ETABS. So in the code, you can check the thickness adequacy using the you have your compressive stress limit. Then this is the compressive stress at left and right, and then this is the compressive stress limit. So basically, the program says that your boundary element having the depth of almost 1 meter. This is for left and right. Okay. So this is the boundary. Then you will just iterate this procedure to come up with this ratio less than 1. Or you can check this one. There is a code provisions that the shear force has its own value. You don't have to, the shear capacity of the wall compared to this shear force demand. This is the demand given by the model or the forces. And in the code, there is a value. I forget the exact formula, but there is a limiting section. So if you have your BU from the forces or from the demand, and from the code, there is a limiting section. There is a limiting section here. Or there is a formula that will yield for the V capacity, that if the BU greater than V capacity, you will need to resize this section. Okay. So this is the end of the video.